So now let's look at resolution limits. The textbook defines resolution limits to mean the smallest dimensions that we can see. So what does that mean? Well, from the previous video, we discussed that light diffracts, and this diffraction actually causes the perceived detail of images to be limited. To understand this better, we have to discuss what aperture is. So let's look at a camera, and the aperture for this camera, we can draw this out. In a camera, the aperture is the opening to the lens diaphragm that determines how much light passes through. So, if I have an aperture that looks like this compared to an aperture that looks like this, obviously this one has more exposure, this one does not have any exposure or very little exposure. So in cameras, it's called f16, this is called f2.8. This is less exposure, and this is more exposure. And the aperture affects how sharp and how blurry the photos will be. So in this more exposure aperture, so a larger aperture, we'll get pictures with a blurred out background, but the foreground is very, very clear. For a small aperture, we'll get pictures that have clarity for foreground and background to be the same. So foreground is equally as clear as the background. Now let's go back to resolution limits. If we have a monochromatic light shining through a small circular aperture, we get a diffraction pattern that looks like this. And in image 1 and 2, we have two adjacent light sources. So in image 1, the point sources are too close together to distinguish between them. And in image 2, the point sources are very, very close, but due to diffraction, you can barely distinguish them. Essentially, improving the resolution reveals that image 1 should actually be two separate sources, as in image 2. In other words, the smaller the aperture, the more difficult to tell whether there is one point source or many point sources. Just like in the camera, if there is a small aperture, the foreground and the background have the exact same clarity. But if it is a large aperture, the foreground is so much more clear, you can definitely tell what's in the foreground compared to what's in the background. This is why professional telescopes have a very, very large, very wide apertures. It's a telescope. Now let's look at Rayleigh's criterion. So Ralyleigh invented a criteria for determining when two light sources are distinguishable from each other. Ralyleigh states that two objects can be resolved if the center of the diffraction pattern overlaps the first minimum of the diffraction pattern of the second source. Now that's a mouthful, so let's draw this out. If you recall, the diffraction pattern would look like this. So this is the diffraction pattern for point source 1. And this is the diffraction pattern for point source 2. Now if you notice, the maximum of point source 1 matches the minimum of point source 2. The maximum of point source 2 matches the minimum of point source 1. This means that these two are resolvable. Why? Because Ralyleigh states that this overlap distance, if this is the bare minimum distance that the 2 point sources have to be for them to be resolvable. If this distance is smaller than this, then it's not resolvable. So the maximum of point source 1 has to overlap with the minimum of point source 2, creating this minimum distance overlap. Then these two point sources can be distinguishable. Once again, if this distance is any smaller than this, they are not distinguishable. Now Ralyleigh had an equation for this, and this equation was sine theta is equal to 1.22 lambda over d. Lambda is the wavelength, d is the diameter of the aperture. So if you recall from simple pendulum physics, we were able to use the small angle approximation for sine theta. So sine theta is approximately equal to theta. Again, we can do that here. If we use the small angle approximation, then we have theta is equal to 1.22 lambda over d. And this is Rayleigh's criterion.